in the last lecture, we were looking at the structure of a turbulent flow in a pipe. Okay, as I told you that in a turbulent flow, there are large velocity fluctuations in all three directions due to the correlated motion of parcels of fluid called eddies. These eddies have a range of sizes all the way from the large scale, that is the flow dimension. In the case of a pipe, that flow dimension is the pipe diameter, down to a small scale. Okay, and we were trying to estimate what was that small scale in a turbulent flow. So, first I had derived an expression for the power input in a turbulent flow. That is just equal to the product of the pressure difference and the volumetric flow rate. And rather than working with the power, which is an extensive quantity, we had defined a power input per unit mass. Okay. And that is equal to delta P by L times the average velocity divided by the density, or I had written it for you in terms of the friction factor, okay, 2F times VAV square, I am sorry, average velocity cubed divided by the diameter. Now, the power input per unit time, okay, per unit mass, okay, the power input per unit mass, which is the energy input per unit mass per unit time, has also got to be equal to the energy dissipated in the flow per unit mass per unit time, which I had labeled using the symbol epsilon. Okay. And for the flow in a pipe, we had got that epsilon is equal to 2F into the V average velocity cubed by the diameter, which scales roughly as V average cubed by diameter. Okay. Now, if the Reynolds number is very high, then you would expect that there will be a range of sizes of eddies, and we were trying to estimate what will be the size of the smallest eddies in this flow. Okay. And that estimate was based upon what is called the Kolmogorov universal equilibrium theory. That is, that the size of the smallest eddies is so much smaller than the large scale, the pipe diameter or the flow velocity. Okay. So, an eddy that is at a particular location in the pipe, which is of much smaller dimension than the diameter of the pipe, cannot depend, the size of that cannot depend directly on the maximum velocity or the average velocity, okay, because that velocity is varying over a large scale. Okay. It does not change the local environment around that little eddy, okay. And therefore, the size of the velocity or the time scale of the smallest eddies cannot depend directly on the average velocity or the diameter. It does, however, depend upon the energy dissipation rate per unit mass, because that energy dissipation rate per unit mass is what has to be dissipated in the smallest eddies. So, it has to depend upon the energy dissipation rate per unit mass with dimension length square T power minus 3, and it has to depend upon the mechanism of dissipation, which is the kinematic viscosity, okay, with dimension length square T inverse, or the momentum diffusivity, because this is what results in the dissipation of energy. Okay. So, because of that, the smallest scales can depend only upon epsilon and nu. Okay. And from dimensional analysis, we had determined what was that dependence on nu and on epsilon for the Kolmogorov length scale, the time scale and the velocity scale. The ratio of the Kolmogorov length and the pipe diameter is R e power minus 3/4. Okay. So, at very high Reynolds numbers, the length scale of the smallest eddies is actually much smaller than the pipe diameter. Okay. We will come back and estimate a little bit what that is. The time scale is also much smaller than what is called the integral time. Okay. The integral time for a turbulent flow, okay, is, well, one definition of the integral time is just based upon dimensional analysis. The diameter times divided by the average velocity gives you a time scale. This is the only time scale that depends upon the diameter and the average velocity. So, the ratio of the Kolmogorov time scale divided by the average diameter, I am sorry, the large time scale is r e power minus half. Therefore, the turnover time of these small eddies is r e power minus half times the time scale for the large flow. And finally, the velocity scale for the smallest eddies is equal to r e power minus 1/4 times the velocity scale for the large flows. So, these we just got on the basis of dimensional analysis. Okay. What are the ratios of, for example, the Reynolds number? Okay. The Reynolds number for Kolmogorov scales. Okay. R E is equal to, in this case, the Reynolds number, if you define it on the basis of Kolmogorov scales, will be the Kolmogorov length times the Kolmogorov velocity divided by the kinematic viscosity. Okay. So, this is equal to the Kolmogorov Reynolds number, the Reynolds number based upon the Kolmogorov scales. So, I can substitute for the length and the velocity from here. Okay. This is equal to, or I should rather say this scales as, okay, it is not an exact relationship. None of these are exact relationships. Okay. There are always factors of order 1 that I have neglected in all of these calculations, such as the friction factor that I did not include, okay, when I defined the energy dissipation rate. So, these should be just taken as scaling relations, order of magnitude relations in the limit as the Reynolds number goes to infinity, and not as exact equalities. Okay. So, this is r e power minus 3/4 times d into r e power minus 1/4 into the average velocity. Divided by nu, okay, which goes as r e power minus 1 into d v average by nu. Okay. D into v average by nu is the Reynolds number. So, this basically goes as 1. Okay. The Reynolds number for the smallest scale eddies is of order 1. Okay. The largest scale eddies have a Reynolds number which is the same as the flow Reynolds number. The smallest scale eddies have a Reynolds number that is 1. Okay. So, the ratio of the Reynolds number of the small scales and the large scales goes as R E inverse. Okay. The small scales have Reynolds number 1. Okay. What is the kinetic energy per mass? Okay. Okay, so, I will write it separately for the large scale and the Kolmogorov. Kinetic energy per unit mass. Okay. For the large scale, it is of course equal to half rho v square. Okay. So, that is the kinetic energy per unit volume. Okay. The kinetic energy per volume is equal to half rho v average square. So, if I want to get the kinetic energy per unit mass is equal to half v average square. Okay. I have to divide by the density to get a kinetic energy per unit mass. So, this scales as the average velocity square. Okay. It scales as the average velocity square. What about the kinetic energy per unit mass for the Kolmogorov scales? Okay. This will go as the Kolmogorov velocity square. Okay. And since the Kolmogorov velocity is equal to r e power minus 1/4 times the average velocity, this goes as r e power minus half times the average velocity square. Okay. Therefore, the kinetic energy in the large scale flow is per unit mass is V average square, whereas the kinetic energy in the Kolmogorov scale flow goes as R e power minus half times V average square. That means that the kinetic energy in the Kolmogorov scale flow is much smaller than the kinetic energy in the large scale flow. Okay. And what is the dissipation rate? Per unit mass. Okay. Note we had got the dissipation rate per unit volume as d is equal to mu times partial Vx by partial z the whole square earlier. Okay. This was the dissipation of energy per unit volume. Okay. I want a dissipation rate per unit mass, an intensive quantity. Okay. That will be mu by the density, okay, divided by mass per unit volume, get a dissipation rate per mass. Okay. Okay. So, therefore, this for the large scale flow will scale as nu times V average square by d square. Okay. The velocity the velocity gradient dVx by dz will have dimensions of velocity square by length square. In this case, the velocity scale is the average velocity, the length scale is the pipe diameter. Okay. So, this scales as nu times V average square by d square. Okay. What about the rate of dissipation of energy per unit volume in the Kolmogorov scales? Okay. I will go through this. When I get the answer, it will sort of be clear why it is obvious. Okay. This is equal to, or I should rather say this is a scaling relation, nu times V k square by L k square. Okay. And V k is equal to R e power minus 1/4 times V average. Okay. So, is equal to nu R e power minus half V average square. Okay. And L k is R e power minus 3/4 times t. Okay. So, I will get by R e power minus 3 by 4 times, sorry, 3 by 2 times d square. Okay. Let me clear that half here. That is what you would estimate. Okay. So, I have an R e power minus 3 by 2 in the denominator and R e power minus half in the numerator. So, this is basically the Reynolds number into nu V average square by d square. And if I substitute for the Reynolds number, I will get Reynolds number is V average d by nu into nu V average square by d square. Okay. And you can easily verify that this is V average cubed by d, okay, which is the same as epsilon. Okay. The rate of dissipation of energy per mass is the same as the rate of energy input at the large scales. So, all of the energy that is being put in at the large scales is being dissipated at the small scales. Okay. And this is also equal to R e times the dissipation if I use this expression, this is equal to R e times the dissipation in the large scales. Okay. So, So, this is the picture. The kinetic energy per unit mass is primarily in the large scales. The kinetic energy per unit mass in the small scale is r e power minus half times the kinetic energy per unit mass in the large scale. Therefore, most of the kinetic energy is in the large scale. Okay. The small scale kinetic energy is much per unit mass is much smaller than the kinetic energy per unit mass in the large scale. However, the dissipation rate in the small scale is much larger by a factor of R e, where in the limit of high Reynolds number. The dissipation rate in the small scale is much larger than the dissipation rate in the large scale, and the dissipation rate in the small scale is comparable, is equal to the power that is put in at the large scale. So, the picture we have is that there is a range of sizes of eddies all the way from the large scale down to the Kolmogorov scale. Okay. Energy is put in at that large scale. Okay. The dissipation rate at that large scale is much smaller than the energy that is put in. Energy input per unit time is much larger than the dissipation on the large scale. However, the flow spontaneously creates smaller and smaller scale eddies. Okay. The flow spontaneously creates smaller and smaller scale eddies down to the smallest scale, which is the Kolmogorov scale, okay, down to the smallest scale, which is the Kolmogorov scale, such that even though the large scale Reynolds number is high, okay, the Kolmogorov scale Reynolds number is order 1. Okay. The Reynolds number based upon the Kolmogorov length and velocity scale is order 1. Okay. So, the smaller scales, the size and the velocity are such that the Reynolds number is order 1 at that smaller scale. So, that energy dissipation is comparable to the energy that is input at the large scale. Okay. The kinetic energy is primarily in the large scale motion, comparable to the pipe diameter. Okay. The kinetic energy in the small scale flow is much smaller than the kinetic energy in the large scale motion, comparable to the pipe diameter. However, the dissipation rate in the small scales is much larger than the dissipation rate in the large scale flow. It goes as Reynolds number times the dissipation rate in the large scale flow. So, kinetic energy is primarily in the large scale flow, dissipation is primarily in the small scale flow, and regardless of what the large scale Reynolds number is, the flow itself creates smaller and smaller scales, such that at the smallest scale the Reynolds number is order 1, and all of the energy that is put in at the large scales is dissipated at this smallest Kolmogorov scale. Okay. This is referred to as the energy cascade. Okay, in a turbulent flow. Okay, this is referred to as the energy cascade in a turbulent flow. Okay. So, if I look at the sizes of the eddies, there will be sizes all the way from the diameter of the pipe for the large scale flow down to the Kolmogorov scale. Okay. So, you will have sizes of the pipe diameter, okay, and so on, okay, a continuum of sizes all the way to the Kolmogorov scale. Okay. And the smallest scale size is the Kolmogorov scale. Okay. Energy that is put in the large scale flow, the energy rate of energy input per unit mass, okay, or the power input per unit mass, that is transferred sequentially down to smaller and smaller scale motion, okay, until at the Kolmogorov scale it is dissipated by viscous friction. Okay. So, the flow itself creates structure of smaller and smaller size, such that at the smallest size whatever energy was put in at the large scale is dissipated due to viscous dissipation. The flow itself creates these small scales, such that even though the Reynolds number for the large scale flow is large, for the smallest scale the Reynolds number is order 1. Okay. So, the motion for the smallest scale eddies has a Reynolds number that is not large, okay, that is order 1. such that inertia and viscosity are comparable for the smallest eddies, even though inertia is much larger than the viscosity for the large scale flow. Most of the kinetic energy is in the large scale flow. However, the dissipation of energy occurs primarily in the smallest scale eddies, okay, the Kolmogorov size eddies. Okay. And because of this, whatever power is input at the large scales ultimately gets dissipated, because the flow itself creates smaller and smaller size eddies, such that all of the energy that is put in at the large scale is dissipated. So, that is the structure of a turbulent flow, and it is because you have these eddies of different sizes, okay, that the fluctuations caused by these eddies result in convective transport, which result in very high dispersion in a turbulent flow. So, if you recall, I had told you earlier that turbulence is a continuum phenomenon. Okay. That is, the size of the smallest eddies is always much larger than the molecular sizes. Okay. We can estimate what is the size of the eddies and the molecular sizes if we take, for example, a flow in a gas, for which we know that the molecular size is the mean free path and the molecular velocity is the root mean square temperature. Okay. So, the molecular length scale is the mean free path in a gas, and the molecular velocity scale is the root mean square fluctuating velocity, the root mean square molecular fluctuating velocity as distinct from the root mean square of the turbulent fluctuating velocity. The turbulent velocity is a flow property. Okay. The turbulent fluctuating velocity is a flow property, whereas the molecular fluctuating velocity is a fluid property, okay, at a given temperature and pressure in general. Okay. So, what is the ratio of the Kolmogorov scale divided by the mean free path? Okay. The Kolmogorov scale, I had told you, was nu cubed by epsilon power 1/4. Into 1 over the mean free path. Okay. For epsilon, I can substitute v cubed by d, okay, nu cubed So, I have just substituted for epsilon. Okay. Let me just write it here. The kinetic energy per unit mass, I am sorry, the rate of dissipation of energy per unit mass. Okay. So, I can simplify this. Okay. So, I will write this as VAV d by nu whole power 1/4 into okay. I have a nu cube, therefore, I will get a nu by lambda and VAV. Okay. I have just rearranged this equation. You can easily verify that it will reduce to this. Okay. So, I have a 1 over lambda here. The power of nu is nu by nu power 1/4. Okay. The power of nu is nu by nu power 1/4. Okay. Therefore, I get a nu power 3/4 here, and the power of velocity is velocity power 1/4 divided by the velocity, that is velocity power minus 3/4, which is the same as it is here. The reason I have written it in this form is because this can be written as VAV d by nu power 1/4 into VRMS lambda by lambda V average. Okay. Recall that from kinetic theory of gases, the kinematic viscosity, the momentum diffusivity, the mass diffusivity and the thermal diffusivity are all scale as the product of the root mean square velocity and the mean free path. All of these scale as the product of the root mean square velocity and the mean free path. And therefore, these cancel out. This first term here is a Reynolds number per 1/4. This is the large scale Reynolds number, not the Kolmogorov scale Reynolds number. So, this scales as the large scale Reynolds number per 1/4. Let me just write it here. And I have here Vrms by V average. Note that the Mach number is the flow velocity divided by the speed of sound. The Mach number is equal to the flow velocity divided by the speed of sound, and the speed of sound is comparable to the root mean square of the molecular fluctuating velocity. The speed of sound is comparable to the root mean square of the molecular fluctuating velocity. Therefore, this Vrms by VAV is equal to 1 over the Mach number. So, this goes as Re power 1/4 divided by the Mach number. Now, clearly for an incompressible flow, the flow velocity is much smaller than the molecular velocity for an incompressible flow. Therefore, the Mach number is small, the Reynolds number is large. Therefore, the ratio of the Kolmogorov scale and the mean free path is large. So, therefore, the length scale for the Kolmogorov flow is much larger than the length scale for the molecular motion or the mean free path. Now, you can do the same thing for the time scales. You can do the same thing for the time scales. The Kolmogorov time divided by the time for molecular motion, lambda by Vrms. The time scale for the molecular motion can depend only upon the length, the mean free path and the root mean square velocity. Therefore, the ratio lambda by Vrms is a molecular scale. Time scale for the Kolmogorov scales, we had got that from dimensional analysis over here, nu by epsilon power half. By lambda by Vrms. For epsilon, I can substitute V cubed by d. So, I will get rho d by V average cubed per half into Vrms by lambda. So, once again I can write this as V average d by nu whole power half into Vrms into nu Vrms by V average square lambda. So, you can easily verify that the dimension of diameter is the same in both of these cases. Nu, I have a nu in the numerator and a nu power half in the denominator, and that is the same as nu power half here. And then I have an average velocity square in the denominator, average velocity power half in the numerator. So, that is V power minus 3 by 2, which is the same as it is here. So, it is just this equation just rearranged. So, this is equal to, I will take one more step, V average d by nu whole power half into the kinematic viscosity is Vrms times lambda. So, I will get Vrms by V average the whole square. Okay. I am sorry, there is no half here, the whole square. Okay. Note that nu is equal to Vrms times lambda. Okay. Nu is Vrms times lambda. Okay. So, I substitute Vrms times lambda here. So, I will get Vrms square divided by V average square, and you can easily verify that this is equal to Re power half by Mach number square. Okay. In the limit where the Mach number is small and the Reynolds number is large, this is also a large quantity. Therefore, for incompressible flows, for gas flows in this case, I have shown you that the length scale, Kolmogorov length by the mean free path is always a large number for an incompressible flow. Similarly, the Kolmogorov time divided by the molecular characteristic time scale is a large number. And of course, in the case of liquids, the molecular scale is smaller still. Okay, the molecular scale for a liquid is much smaller than that for a gas. And therefore, for fluids in general, the ratio of the Kolmogorov scale and the molecular scale is always much larger than 1 for a incompressible flow where the Mach number is small. And therefore, turbulence can be described by the continuum approximation. Okay, so I just went through this calculation to show you that the turbulence can always be described by the continuum approximation, because the length and time scales are always much larger than the length and time scales for the molecular, okay, for the motion of the molecules. So, this is a brief description of turbulence, a general description of the structure of turbulence. Okay. In a pipe where we had calculated the energy dissipation rate as a function of the power input per unit mass. Okay. I will talk a little bit next lecture about how these turbulence structures depend upon position in the pipe, okay. Especially the near wall behavior of these for these turbulent flows. So, I will continue this in the next lecture. I will see you then.